A walk is a sequence of vertices linked to the next vertex by a specified edge of the graph. Okay, so basically it's just like, imagine, you're like trying to walk somewhere, and if it's possible to go from B to D, that's a walk. Okay, I can go from B to D and to C and then back to D if I want to. Just if it's possible to do, that's a walk. Okay, and so think about what's not possible to do. If you're on E and you want to go to C, that's not possible, at least directly. Bless you. Okay, so a walk is just something that's possible, I suppose. A path is a little bit more specific. It's a walk that uses no edge more than once. So if I wanted to go from B to D and then back, that doesn't count as a path. Okay, think about it as bridges. As you travel across a bridge, you burn it, so you can't use it again. All right, that's a path. And a circuit is going to begin and end at the same place. It's a path that begins and ends at the same place. So if I go from A to B to C and back to A, that's a circuit. Okay, but it's a path, so I can't use the same edge more than once. So as long as I do that, that's a circuit. So, check out those definitions. Make sure you've got a firm grasp on them because it's a little bit tricky sometimes. Number 8 says, classify each sequence in the graph as a walk, a path, or a circuit. So we look at E to C to D to E. And if you notice, we can't even do that. We can't go from E to C. That's going to be impossible. So that's not even a walk. And if it's not a walk, then it can't be either of the other two. The next one says A, C, D, E, B, A. So A to C to D to E to B to A. Now that started and ended at the same place. That probably makes it a circuit as long as it didn't use any edge more than once. Okay. Well, if it's a circuit, it must be a path. And if it's a path, it must be a walk. So that's yes to all of them. B, D, E, B, C. B, D, E, B, C. Okay, well, that's not a circuit because it doesn't end where it started. I guess, is it possible? If it's possible, then okay, it's possible. So it's a walk. Does it use anything more than once? It does? Don't think about the B. I don't care about the B. I care about using edges. The edges are the bridges. Okay? So I'm not burning any bridges, so that must be a path. That is a path. Okay? I can go to the same vertex more than once. I just can't burn bridges and use it again. Okay, so then we've got A, B, C, D, B, A. A, B, C, D, B, A. Aha. See how I'm trying to use that same edge more than once? That's not a path. Okay, but it is possible. Okay, it is possible to do, so that makes it a walk. I ended up where I started, but I'm not allowed to use that same bridge again, so that's not a circuit. Okay, it doesn't count as a circuit. I know that question's kind of tough, so you might want to go back and look at that again. A weighted graph is a graph with numbers on the edges. And so what this is this really is the same. It's the same picture as that Green Bay. It's the same picture as this. But they threw in weights, and specifically these weights are talking about like the time it's going to take for the bus to get from one city to the other city. Okay. So when they do example 9, it says which is the quickest path from Grand Forks to Escanaba. That's a really useful thing to be able to do. And so I want to go from Grand Forks to Escanaba. And so, if I look at this, obviously I'm going to have to go through Minneapolis. And I can kind of break this into two legs, but I can see this leg of the trip is going to be faster than if I went this way. Okay. And that's, what is that? 7 hours and 10 minutes if I go that way. And then, after Minneapolis, I can either go up here or down here. It looks like if I go this way, that would be 8 hours and 45 minutes. That's going to give me my quickest route. If I go Grand Forks to Fargo to Minneapolis to Green Bay to Escanaba, that's going to be the fastest thing. And if you add those two numbers up, that's 15 hours and 55 minutes. A complete graph is a graph with exactly one edge from each vertex to every other vertex. So I think that definition seems kind of complicated, but once you draw it, you'll be fine. Draw complete graphs K4 and K5. Well, K4, think of it this way. A K4 has 4 vertices. Usually I'll draw them in a box. It doesn't have to be in a box, but that's usually what I'll do. But what happens is K stands for complete, and that makes me think that each of those dots is connected to every other dot. Okay? So what you want to do is just make sure you draw a line from each dot to every other dot. That's a K4. Notice the degree of every vertex is what? 3. Now let's do a K5. A K5 is going to have 5 vertices. And again, it doesn't really matter what shape you pick or what shape you make them. I'll do a pentagon. But all 5 dots are connected to all 4 other dots. Notice the degree of each of those dots is 4. There's the K4, there's the K5. Complete. Number 11, in a round-robin tournament, every contestant plays every other contestant. The winner is the one who wins the most games. Suppose 6 tennis players compete in a round-robin. How many matches will be played? Okay, so think about it. There are 6 players. Each of those 6 players would play the other 5. Each of those lines represents a match. So essentially, we're going to draw a K6, and we want to count up the edges. Every dot has to be connected to the other dots. One way that I check my drawing is make sure that every one of the 6 dots has a degree 5. I think that's it. Okay, that's a K6. But we want to know how many edges there are, and I think it kind of makes my eyes go crossed to count them. But if you think about it, there are 6 dots, and we want to choose 2 of them that are connected. We want to see how many connections there are, and 6 choose 2 equals 15. That's the answer. Other way of answering this is to count those edges. If you could count those edges, and you probably can, if you could count those edges, there's 15 of them.